Good afternoon, ladies and gentlemen. Today, my group and I will be presenting on a concept design of a class of high-speed crew transfer vessels. This design was produced by a team of 4. The first member of our team is Gunnar from Cohasset, Massachusetts. Next, we have Rayne Duff from the Virgin Islands. Then myself, coming from Torrance, California. And finally, Burke Kanemasu from San Diego, California. Before I continue further, I would like to thank our industry mentors, as well as Professor Golden, for their help throughout the design process, as well as the crews of Windea Intrepid and Gateway Endeavor for allowing us to tour their vessel. In this presentation, we will describe vessel requirements and objectives, and introduce you to the design through its particulars and characteristics. We will then provide a detailed description through its arrangement and optimizations, and we will discuss the weights and centers as well as the stability. And finally, we will discuss the structures and vessel systems we used. And finally, we will conclude with time for questions. Now on to mission requirements. The image depicts the final goal of our high-speed CTV, the delivery of technicians and cargo to offshore wind farms. To do this, our vessel had some functional requirements, such as being able to carry 30 technicians to wind farms located off the American East Coast, in sea states of up to Beaufort Sea State 4, which includes waves of significant height of 5 feet and winds up to 16 knots. In addition to our functional requirements, our vessel has a few performance requirements set by its owners, which include a sprint speed of 25 knots and the ability to carry up to 20 long tons of deck cargo and remain in the operating field for up to 5 days. Beyond those requirements, our vessel must also carry a complement of 4 crew members in addition to 2 officers, and provide a workshop space for technicians to work on gear or small turbine parts prior to boarding the turbine. Our vessel design is also subject to a variety of constraints, such as a 100 gross registered tonnage limit under the standard system, and a draft limit of 10 feet, as well as a 25% reduction in conventional fuel use to remain environmentally sustainable. Our vessel is also subject to many regulatory bodies, such as Class NK, a Japanese class society with rules on small vessels and high-speed craft. We are also subject to US regulatory bodies, such as the Code of Federal Regulations, Chapter 46, Subchapter L, as well as international regulations, such as IMO's Intact Stability Code, created in 2008. During the concept design's evolution, many systems were considered. The major systems focused on during this project included hull structure, the propulsion system, bow fendering, a battery and electrical, and of course, passenger seating and comfort. Now I will introduce you to our vessel through its principal characteristics. The CTV we have designed is an aluminum catamaran, the length of 91 feet and 8 inches, with an overall beam of 33 feet with 11.5 feet per hull. It draws a draft of 8 feet with a depth of 16.5 feet, and in its full load condition, displaces 153 long tons with a light ship weight of 94 long tons. It is also designed to operate at its required speeds and fulfills its cargo capacity requirement. This slide depicts our outboard profile and forward view of our vessel from our general arrangements. This view highlights unique features such as our deep axe bow and important clarifications such as the cargo container placed on the foredeck representing our max cargo load. This is our inboard profile. A large portion of our design hinged around the location of our technician or passenger seating. This section of the main deck has seating for all 30 technicians with 15 on either side of the vessel in rows of 3. This space is placed further aft than it is on many existing CTVs, which may improve technician ride comfort and reduce seasickness in rough weather. Our crew and officers' cabins are located on the cabin deck aft of the pilot house. It was made sure to keep any long-term accommodations outside of the hull in order to maintain crew comfort, as during our visit, it was found that it's very cold in aluminum hulls and is also very loud when underway. Our bridge lies on the pilot house deck, which is slightly raised above the cabin deck, which maximizes visibility over the bow and sides in order to allow the pilot to have maximum awareness during any fendering operations in potentially rough seas, such as coming up to a turbine. Below decks, the inboard profile depicts our engine room, housing our main engines and combination motor generators in a V-drive configuration. In the forward end of our bow, large fuel and potable water tanks are stored in order to support our 5-day endurance, as our vessel does not have a freshwater generator. In addition to that, a few concessions were made due to our visit, such as a lounge, which the crew specifically requested as a good idea and was very popular, and the addition of a technician workshop in the forward end of the main house to allow technicians to work on their own personal gear or parts. I'd now like to invite Rayne up to discuss the main deck.
Thank you, David. This view shows a plan view of the main deck, where the technicians will spend most of their time and work will be done. Important to note on this view is the technician seating, which is positioned close to the windows to provide a better view and reduce seasickness for the technicians. Also important to note is the workshop and wet room spaces. The workshop is greater than 150 square feet to satisfy our design requirement, and also has direct access to the foredeck to make it easier to bring equipment inside and work on it and not have to go around to the side. The wet room provides space for technicians to hang up their wet gear before going inside, so they don't have to bring wet gear inside. And there is also a head in the wet room so that those working outside can come in and use the head without trekking through the entire vessel. Also, you can see on this view the lounge and galley area. These are particularly large because the crews that we visited requested larger lounge and galley areas to make living and working on the boat a little bit easier and a little bit nicer. This view shows the hold deck plan. Important to note on this is the large engine room, which will be discussed further in the presentation. And the governing aspect of the design of this space is the tonnage optimization. There are deep frames located at several different points throughout the vessel that progress outward in to reduce the tonnage counted for our vessel. In catamarans, it's particularly important that the part that's included in tonnage is towards the center line of the vessel because the area in between the hulls, or the length between the hulls, is also considered. There's also further tonnage optimization in the other areas of the vessel. We have tonnage openings that are with 4-foot wide progression throughout a lot of the main deck, which omits most of it. After all the calculations were done, we still are at 128 gross registered tons. Our requirement is 100 tons. Partially, this was because later on in the design phase, we moved our crew cabins out of the hull and up onto the second deck, which increased the counted tonnage there. And that was a very late design stage decision. So that increased our tonnage, and we will have to, before the final design report, come up with more tonnage optimizations to exclude that space. That being said, we did reduce our tonnage counted from almost 300 tons using the deep frames and the exclusions that we did use. This slide shows a profile view and half breadth plan of the lines plan. Note the deep axe bow, which helps for seakeeping. This shows the body plan of the hull form. The important consideration here was we did widen our hull at a certain point in the design phase to reduce the interference resistance between the hulls. Additionally, most of the hull is designed to be developable so that it can be constructed more easily. There are some areas around the stern which require a little bit more attention to get those to be developable surfaces, but most of it is developable at this point. This shows the midship section. We don't have any longitudinal stiffening here because we're a transversely framed vessel. The shell plating is 5/16 inch plate, which is thicker than typical CTVs this size because of the Class NK rules. Also, with this thick shell plating, we do pass the section modulus requirements with Class NK, which was the structural analysis used for this project. The weights and centers estimations were done for 3 loading conditions: the lightship condition, full load departure, and full load arrival conditions. The hull form was designed such that the full load conditions have an even trim and sit at our design draft. The lightship condition has a slight aft trim. This is due to the removal of the large 20 long-ton cargo load on the foredeck in the lightship condition. That has a significant impact on a vessel that only weighs 92 long tons lightship. So it makes a big difference. This is a visual representation of that shift in center of gravity from removing the forward cargo. You can see the full load center of gravity is farther forward than the lightship center of gravity. The center of buoyancy shown here is at the design draft. That will obviously move depending on where the center of gravity is until the vessel reaches equilibrium. I would now like to invite Gunnar up to talk about the stability of the vessel.
Thank you, Rayne. Our vessel stability. As per the project requirements, the vessel is required to conform to the IMO's International Stability Code, or International Code on Intact Stability, adopted in 2008. The stability analysis was conducted using GHS, or General Hydrostatics. This is the riding arm curve for the full load departure condition of our vessel. On this graph, please note the GM, which is circled, which is greater than 28 feet. Also note the angle of greatest riding arm, which is 22 degrees. These numbers are indicative of a vessel with very high initial stability. This is characteristic for catamarans. These are the floatable length curves for the vessel. Notice that the engine room, the aftmost compartment, satisfies floatable length with a permeability of 0.85. The permeability of the forward compartment between frames 4 and 10 is currently set to 0.95, but due to the large tanks in the space, the actual permeability will be much lower. Still, if judging solely from floatable lengths, it would appear that flooding of the engine room is the worst case scenario. In conclusion, the vessel passes the IMO intact stability criteria for offshore supply vessels, as described in Part B, Section 2.4 of the Intact Stability Code. More simulation is necessary to determine if the vessel passes the damage stability criteria. Again, flooding of the engine room appears to be the worst case scenario. In another iteration, we may consider rearranging the machinery space and the surrounding bulkheads to improve survivability. I'll now discuss our vessel's propulsion system. We selected a diesel hybrid electric power plant because we found it to be a good compromise between capability, reducing underwater radiated noise, and meeting the 25% reduction in conventional fuel use. We decided to utilize a V-drive because it allows for a more compact machinery arrangement, and we also found that to be typical of CTVs with shafted propellers. We also elected to use a controllable pitch propeller to enable best performance in each of our very different operating modes. This includes transit at high speed, electrically powered loitering at low speed, and delivering adequate bollard pull to push on the wind turbines at 0 speed. For the vessel's main engines, we selected the Caterpillar C32. It produces 1,450 brake horsepower and can be made EPA Tier 4 compliant with urea aftertreatment. The Cat 32 is a prolifically produced engine and is used by many different industries. It complies to the Buy America requirements of our customer. And we also found that Caterpillar engines were well liked by the American operators we spoke to because parts are plentiful and it's not difficult to find licensed technicians who can work on them. For the motor generator of our hybrid drive system, we selected the Transfluid HM2000. In normal operation, the motor generator provides some of the propulsion power and all the electrical generation needs of the vessel. It is connected directly to the flywheel of the main engine and has its own bridge-operated clutch. The motor generator is capable of producing around 400 brake horsepower at the intended RPMs. However, it will rarely be used at full power due to the loitering operating profile. This is a marinized derivative of an established land vehicle hybrid system, so it's not unproven. The Z drive we selected is the ZF8000V. It features an 8-degree V and is capable of handling the peak power output of both the main engines and the motor generator simultaneously. This would be an unusual operating mode, but it is considered nonetheless. I'd now like to invite Burke Kanemasu up to the stage to discuss our bow fendering system and operating conditions.
Thank you, Gunnar. All right, the active bow fendering system. The main purpose of this system is to keep the bow connected to the turbine during our crew transfer operations. This is done by way of notches that made up with the vertical posts on the turbine, and also the hydraulic pistons shown in the figure also serve to dampen the impact loads with the posts on approach through the hydraulic pistons. Additionally, the pistons allow for sort of wiggle room to keep the vessel connected firmly, even in larger waves. So, going over our operating conditions. Our first primary operating condition is our loitering condition. This is when our vessel will be waiting at the turbine field for the technicians to finish their work. In this condition, we are fully electric and our engines are completely turned off. This is how we plan to meet our 25% reduction in conventional fuel use. Our next primary operating condition is our cruising or transit condition. Now, this is when we're going out to the turbine field and back. In this condition, our main engines are not only powering our propulsion, but also charging our batteries. So that brings us into our electrical system. Our electrical system can be split into 4 main categories. The first category, generation, includes our shaft generators, as we've discussed, and the emergency diesel generation. There's also consideration for future cold ironing directly from the wind turbines. The next category is storage. This includes battery rooms in each of the 2 hulls. Also, we have distribution, where we have switchboards in each of the pump rooms, and also a main DC bus. The specifics of our unique distribution system will be covered in the following slides. Finally, we have our loads. This includes our propulsion loads in our loitering condition, and also our hotel loads in all of our conditions. All right, this brings us into our section of our one-line diagram where you can see some of the notable features that I just mentioned, starting with the main DC bus. This DC bus is fed by either the motor generators or the battery bank, depending on our operating condition. It supplies the motors in loitering and the batteries in transit condition, and also always supplies that 480-volt AC switchboard that can be seen below. Speaking of this 480-volt AC switchboard, this is fed by that DC bus, or it can also be fed by the emergency diesel generator in an emergency condition. When we are in port, it can be fed by shore power, or as we mentioned before, by the actual wind turbine during our mission condition. This will supply a 120-volt panel and a 240-volt panel. Our electrical plant load analysis shows our cruising condition, our mission condition, and our emergency condition. It also splits each of those conditions into a summer and winter category. As you can see, the cruising condition contains the highest load, and specifically the winter cruising condition due to its slightly higher lighting, HVAC, and miscellaneous equipment loads. In conclusion, our vessel satisfies the owner's requirements using the 25% less fuel than other similar vessels. And that being said, it's still a very preliminary design. So a lot of things, as we mentioned, will be fixed in the next lap around the design spiral. Here are our references for the presentation. And I'd like to thank you all for your time. And at this time, I'd like to invite the rest of my group back to the podium to take any questions that you might have.
The bike plan you put up seemed to be a slight tunnel in there. Oh, can you discuss the reason for that? It didn't look like it was necessary to travel.
Yeah. So the question was why there was a propeller tunnel when it wasn't necessary for draft limitations. The reason for this was mostly the angle of the V drive. It made it so that we could mount the engine in the way that we did with the space that we had available. Also, our propeller was a 1 meter approximately diameter, which is quite large. So we needed to make space for that with the shafting arrangement that we had.
So, I mean, obviously designing a catamaran is all different than designing a monohull. What was the biggest challenge you faced when going with the catamaran design for your vessel?
The question was, what are some of the challenges we encountered in designing a catamaran? One challenge we did have was space in the holds inside the hulls. That was particularly problematic when we're designing our machinery space, just because they're so narrow. And so the space requirements, we were pretty constrained for our machinery. You guys have anything to add?
Yeah, I would also add the stability was interesting because particularly for our angle of maximum righting arm occurred quite early. So typical ships, it was greater than 25 degrees, and ours occurred basically exactly at that at our full load, which is quite a bit different than typical models.
Another thing to add to that again is the transfer between the main deck and the hulls, especially specifically with like staircase locations. Following Class NK rules require certain angles, certain types of upwards passageways, and fitting that in with maximizing space in the hulls was very, very hard.
Is the need to make or attach to the structure of the wind turbine what differentiates this vessel from an offshore cruise boat in the oil industry? Because other than that being up against that structure, the mission requirements look quite similar.
So the question was, what are the different requirements between offshore wind turbines versus offshore oil truth transfer boats? The answer to that is generally the actual setup for how you get onto the platform. With offshore oil, you can generally rely on people on the rig itself to lower transfer equipment such as cranes or man baskets and lift them up. With this is our vessel is the only piece of equipment the technicians can rely on to transfer onto the turbine. So the system that has been designed and standardized is that post system where notches in our bow can be made up with those and allow them to transfer onto a ladder or any other climbing equipment to get into the turbine itself.
Thank you.
Yeah, I'm just curious if you had any consideration of global squeeze pilots on the wall for the design and prospect structure.
So the question was if we considered the transverse squeezing loads from having a catamaran hull. And for the purposes of this design, we looked at longitudinal strength primarily. I know that's mostly applicable for larger, longer ships, but for the purposes of the academic exercise, that's what we looked at. We did not, it was outside of the scope currently to look at the transverse loading.
I'm not too familiar with the catamaran design, but is it typical to have the deepest part of the hull, the furthest forward?
The question was, for a catamaran like this, is it typical to have the deepest part of the hull furthest forward? And so that configuration is called an axe bow. And what it does is the bow up forward is very narrow. And so it's very deep to provide the buoyancy there. And what that does is because I guess the plane that's at the same surface of the water is very narrow, it reduces the pitching accelerations, which improves the ride quality for the technicians. So it's mainly for seakeeping and comfort. And we found them to be typical, axe bows to be typical of CTVs that operate in the North Sea. where the sea state can be very violent. So we decided to incorporate it into our design for the North Atlantic, the American East Coast.
So I thought it was very good that you did early incorporation of operations. So that it really liked people. Areas. One question, same thing that I asked the first group. What do you feel like are the key areas for the next trade studies that you would want to work with your clients to go to the next stage?
Yeah, so the question was, what are the key areas that we would ask our clients to debate and evolve the design? The biggest challenge was the 21 tons of cargo. When we visited crews, they basically never carry that. Like, they're all designed to carry that, but they basically never carry 21 tons of cargo on the foredeck. Mostly they're carrying like crew bags, which can be like around 1,000 pounds. So they're they're very rarely carrying that. So I would ask them to lower that requirement.
You realize that probably a ton or so that is going to sound.
Provisions were accounted for.
Yeah, concerning that outside of the arrangement savings on going to the egress solution.
Yeah.
Were there any considerations operational going towards a high propulsion system or a waterhead propulsion system?
So the question was, what were considerations with going with a shafted or V-drive propulsion system instead of a podded propulsion system? One other system that's typical for CTVs that operate on the East Coast is the Volvo IPS pod drive. One of the requirements of our customer was that the main engine had to be American built. And a lot of the pod or like the azimuthing drives are designed to work with a proprietary engine that often wasn't built in the United States. And so to meet that requirement and to make it such that technicians who were licensed to work on the equipment were more available, we decided to go with the shafted arrangement because it was a bit simpler. One thing we would consider for the next go around the design spiral is we consider actually removing the V drive and doing a simple straight shaft to just make our machinery space more accessible and less cramped in the aft of the vessel. That's one thing we would consider. Something else that our mentors recommended was possibly going to 4 shafted propellers, 2 of them being straight shaft, 2 of them being V drives, to bring us under the 800 horsepower minimum, or basically put us at tier 3 emissions compliance instead of tier 4. So long story short, there are a lot of considerations, but we did decide to go with the Z drive for now to have a small machinery space and make it such that it could be easily maintained.
You mentioned that you've selected 2 40-inch diameter controllable pitch propellers. Have you found a commercially available 40-inch controllable pitch propeller? If you have, is the Z drive that you selected, the ZFB drive rather, you selected compatible controllable pitch propulsion?
So the question was our propeller design sourced at all? And the answer is that we didn't. That was not within the scope of our project. The propeller dimensions were size based off propulsive efficiency in a NavCat analysis for propulsion and resistance. And the series we used was a GON KCA series, which does have controllable pitch options available, either from custom or like kind of series based. However, we did not look at compatibility between shafts or production or source of that propeller.
Small line questions. One question was just if you could explain a little bit more what drove the decision to move the crew spaces out of the hull.
Yeah, so the question was what drove the consideration to move the crew spaces out of the hull and onto the cabin deck. So this was mostly a comfortability consideration. When we visited a similar vessel, they said that the hulls would be loud and very uncomfortable, very cold to live in due to aluminum's very low insulating properties. And so after actually being in the hulls also ourselves, we noted that it would not be a suitable place to sleep and to live. So we decided to move those up to the cabin deck.
Next question here. Is there a plan for a spray rail on the lower chine boat separation?
Yeah, so the question is if there was a plan for a spray rail on the lower chine for mode separation. That lower chine was actually added relatively late after we realized we needed more buoyancy forward for the forward cargo. So at this stage, it doesn't, but it could have in the future with the future iteration. And the hull is definitely at a preliminary phase.
Okay, next question, yeah, we've got a few on. What 480 volt consumers are there on the shipboard side driving that voltage requirement?
Yeah, sure. So the question was, what 480 volt loads are present on our ship and our one line? One of those requirements is actually a fuel transfer pump. So one thing that the wind turbines require with occasional maintenance is they do have diesel generators on board to serve as emergency generators to run systems, cranes during construction, and as a backup to the shore connection and the wind turbine itself. So diesel fuel does need to be delivered occasionally to the wind turbines. So we do have a fuel transfer pump on board to do that, and that's one of our 480 volt loads. Also, there is a fire pump, another 480 load, a 480 volt load. Are there any others? You can just think of it. Sorry. I think that's all off the top of our heads for now.
Okay, well, there's one last question online for now. Does the vessel weather vane, or is there one orientation on the wind turbine mast?
So the question was, does the vessel sort of weather vane around the wind turbine, or is the position of the wind turbine posts fixed on the turbine? And for the turbines that exist currently, all the posts are fixed in one orientation. So this doesn't see, when we talk to operators, this didn't seem to be an issue with the bollard hull capabilities of the vessels. It seems that a very stable connection can be maintained even in seas and winds coming from any direction.
Any other questions? Okay, thank you very much.